Earlier we were discussing Schrodinger equation in one dimension. Today we shall start linear harmonic oscillator. It is also a one-dimensional problem, but because of its importance in physics, we will record it under the heading linear harmonic oscillator. Firstly, I want to mention what is the importance of studying linear harmonic oscillator. It is one of the rare problems in physics which is exactly solvable in classical mechanics, as you have seen, and we shall show that it is also an exactly solvable problem in quantum mechanics. This is first important. Exactly solvable problem. In classical as well as quantum mechanics. Secondly, Fourier theorem enables us to express even an aperiodic motion as a combination of simple harmonic motion. Fourier theorem. Complicated motion can be looked upon as a combination of simple as a combination of simple harmonic motions of varying frequency, fundamental and the other harmonics. Second, in many particle systems, there is a technique called normal modes. Where each of the mode is an LA. If you consider a solid comprising of a large number of atoms, then these atoms are interacting among themselves. If the interaction for small separation can be considered to be an harmonic linear force, then it can be shown that the system in normal mode analysis if the system comprises of n particles, then after normal mode analysis the system decouples or reduces into n independent harmonic motions called the normal modes. This is the most important thing about linear harmonic oscillator. Now I am coming to the definition of linear harmonic motion. It is firstly, it is to and fro periodic motion about equilibrium point. Position. The restoring force is proportional. Restoring force F is proportional to minus x, where x is the distance measured from equilibrium position. Thirdly and most importantly, it is linear motion. This is very important. This criteria restricts ourselves when we consider a motion of a simple pendulum. This condition restricts us for small angle oscillation. This theta is less than 4 degree. This restriction comes from the linearity. So the arc length between plus minus 4 degree can be approximated by a straight line. That's all about the fundamental. Now I come to the classical description of linear harmonic oscillator. A linear harmonic oscillator in classical mechanics is described as the motion of a particle confined between 2 points. If we consider this is the x-axis, then this is the 0 of the x-axis, and particle moves between minus x to plus x. It oscillates between this, and the restoring force that acts on the particle is F is equal to minus kx. Correspondingly, the potential energy is comes out to be half kx square, which can also be written as half omega square x square, where omega square is equal to k by m. K is the spin constant and m is the mass of the particle, and omega is the angular frequency. Then this is the particle moves to and fro between plus minus x. The range x increases with increasing energy, and if we like to draw the energy diagram is like potential energy is a parabolic function. It should be symmetric one. Potential energy. This is the total energy of the particle, because at the extremities the potential energy is equal to energy. That is to say, the total energy E is equal to kinetic energy plus potential energy. It can also be written as T max, or it can be written as V max, where V max arises over at the extremities and T max arises at the center. The kinetic energy, this is the potential energy curve. The kinetic energy curve is just this. This is the kinetic energy part, and this is total energy of the particle. If we consider the region to the right of plus capital X or to the left of the mark, here the kinetic energy is negative. In this two region, kinetic energy is negative. So the classically particle cannot go beyond plus minus x. It remains confined in plus minus x. What happens to the motion when the particle approaches the extremities? The potential energy increases and approaches the total energy, and at the same time the kinetic energy decreases, and at this point, coming to this point, kinetic energy becomes negative. Now the particle starts moving towards the other direction. Similar thing happens when the particle approaches the left extremities. Then on coming there, the kinetic energy becomes 0, then particle makes a turning. So these 2 points are called classical turning points. These two are called classical turning points. So the particle remains confined within plus minus x in classical mechanics. And so far the equation of motion is concerned, we know that the motion equation satisfied by this is x double dot plus omega square x is equal to 0. So we write a solution as if we said that at t is equal to 0, x is equal to 0, then we get x at t is equal to sine omega t. The velocity is given by dv dx. Velocity is given by dv dx. Dx dt. So it becomes omega x cos omega t, which can be written as x square amplitude square minus displacement square. Note that this is capital X, this is small x. Now I come to the probability, because in quantum mechanics one talks about position probability. So we want to see what is the corresponding classical prediction. So classical prediction Pc of x dx, it is the classical probability of finding the particle between x and x plus dx. This is given by the time that the particle the time delta t over which the particle is within distance dx divided by total time. So if we consider this, the motion, that if we consider this is the x and this is the with dx, then the particle spends a time dt when it moves towards the right, and spends an equal time dt when it moves towards the left. So we write dt as dx by v, but twice dx by vt, because we write dt as twice x by v. From this relation we know that dt is equal to dx by v, because it travels the strip twice, so the factor 2 is there. And if we write for v this expression, we get twice dx omega t x square minus small x square. As omega t is equal to 2 pi, this is the classical probability. If we draw the graph looks like this. This is plus x, this is minus x, this is a PC. At x is equal to 0, it is a minimum. So it is a minimum and tends to infinity at both the extremities. This is because of the fact that at this point, at the equilibrium point, the particle passes with maximum speed, so the dt is small. And on the other hand, at the extremities, the velocity passes through 0. That's why the particle there is classically there is an infinite probability of finding the particle at the extremities. Whenever you have performed experiment in laboratory with systems having high time period, say of the order of 14 or to 20 seconds, it is found that the particle passes through the equilibrium position rapidly, and the pendulum comes to almost rest at the extremities. This is the fact. Now I come to the quantum description of the system. Quantum mechanical, since it is a conservative system, we introduce a potential function, and quantum description is this. Firstly, the potential energy. So the time independent, this is the potential energy. So the time independent Schrodinger equation is minus h line square by twice m. Since it is this is a one-dimensional problem, I write it plus v of x psi of x plus e of x. Note that e is positive, or psi of x is equal to e of x, e psi of x. We use a scaling. Scaling is that q is equal to alpha x, where alpha is not equal to 0 and finite real quantity. So we change the independent variable from x to q. So ddx now becomes alpha ddq, and d2x dx2 is equal to alpha square d2q dq2. So this equation together with this becomes x is equal to q square by alpha square. Psi, now here psi is a function of q. Or this term we are right twice m e h line square alpha square minus m omega, this is alpha square, m omega h line alpha square q square psi of q is equal to 0. Psi of q is equal to 0. Now the choice of alpha is entirely on our discretion. In that case it would be better to use second bracket. We choose alpha in such a way that this is equal to 1. Once we have chosen alpha, we have no control on it. Just we to shortcut the notation, we call it lambda. So such scaling, choice of scaling is this. Scaling parameter alpha is that we use m omega h line alpha square is equal to 1, or alpha square is equal to m omega by h line. The significance of alpha will be discussed later. Now the lambda. If we use this value of alpha, this becomes me by h line square and for 1 by alpha we write H line m omega. So on simplification the m cancels out, so this is twice E H line omega. We know from Planck's law that H line or H cross omega is energy that an oscillator emits, and so this is the twice the dimensionless energy. And what is alpha? Alpha square, if you analyze the dimension of alpha square, we find that alpha square is equal to m we multiply both numerator and denominator by omega, so this is the energy and this is omega square. So the dimensional analysis gives you m omega square H line omega. This is energy, so it is m for mass. Omega has inverse of time, so this is -2, and this is energy. L inverse. So the quantity that we have introduced, this is a dimensionless position. So the equation that here in its dimensionless form becomes so the solution of the quantum description of linear harmonic oscillator with the scaling factor, thus with the scaling this where alpha is defined by the relation thus becomes in its dimensionless form as this. So our task is to solve this differential equation subject to the boundary condition that as q, with the boundary condition is that as psi of q as q tends to plus minus infinity must go to 0, because classically the particle is confined between two sub boundaries plus minus capital X, and although there is tunneling effect in quantum mechanics, but the wave in the classically forbidden region we have seen that the particle wave function dies exponentially, so at infinity it must go to 0. So the task of quantum reduces to their solution. The quantum description now becomes H with alpha square is equal to m omega H line, lambda is equal to twice m E by H line omega, and q is the dimensionless position. This is our summary. Now if we want to solve this equation, then using the Provenance method, it is found that if we apply the Provenance method to the equation in this form, the solution is not obtained in a closed form. That is, the relation is not obtained in terms of any known function. So one needs to simplify the equation. So we note the asymptotic solution. Asymptotic behavior. Asymptotic behavior means when q tends to plus minus infinity, in which case this q square term dominates and the equation becomes we want to a solution of asymptotic equation. Trial solution we assume as psi of a is equal to x to the q to the power n e to the power beta q square. The choice of q square is due to the fact that the function must go to 0 at plus minus infinity, so it is q square. Now the first derivative is this part is n into n minus 1 q to the power n minus 2 when we differentiate this term, and when we differentiate this term it is twice beta n plus 1, twice beta n plus 1. This is the q to the power n. This must be multiplied by this, which we will do at the end, and then this part remains intact. Multiplied by twice beta q, and whole thing is multiplied by e to the power beta q square. So on simplification we get n into n minus 1 q to the power n minus 2. This term, if we take 2 beta q common, so this is q to the power n, and if we collect the term, this becomes twice beta 2n plus 1 q to the power n, and finally 4 beta square q to the power n plus 2 multiplied by e to the power beta q square. So if we plug this into the original equation, so we get from asymptotic solution this, and together with this this is the contribution from the double derivative term minus and whole thing is multiplied by e to the power beta by term, which is not significant here. The leading term in this differential equation is this, and beta should be so chosen that this leading term gets cancelled. That is, we from leading term we get four beta square minus 1 is equal to 0. That is, beta is equal to plus minus half, but plus half will make the wave function diverge at the asymptotic region. So physically acceptable solution is beta is equal to minus half. This is the physically acceptable solution. So we get from the this that the wave function behaves as q to the power n e to the power minus q square by 2. This is the lesson that we have learned from the analysis of asymptotic solution. So we now write the solution of the original equation, not the asymptotic equation. So the trial solution for the original equation, which is valid for all values of x, is written like this: psi of q is equal to some function of x e to the power minus q square by 2, with the requirement that f of q with q tending to plus minus infinity is finite, so that when we multiply this finite quantity in asymptotic region with the quantity that goes to 0 is the 0, so that the wave function dies exponentially in asymptotic region. Now our task is to find out the differential equation that is satisfied by f. In that and we differentiate this once. So we get f prime. I am omitting the argument. Then if we differentiate this part, we get minus qf e to the power minus q square by 2. If we double differentiate it, we get f double prime qf prime minus f, this is from the first term, and then f prime minus qf, and whole thing is multiplied by e to the power minus q square by 2. This becomes f double prime, there is 2 minus, and then there is 1f, and this is plus. If we plug this in this equation, we get from this part. I am now ignoring this e to the power part. This is from double derivative part plus lambda minus q square f. This plus q minus q square f and this plus q square f gets cancelled, so we get the differential equation is this. So the solution, quantum mechanical treatment of linear harmonic oscillator now has reduced to this problem. Before that, we see what we want to summarize what we have done. Time independent, time in summary of this class. First, time independent Schrodinger equation has been made dimensionless through the introduction of the parameter alpha square is m omega by h line, so that the differential equation becomes with the condition that psi goes to 0 asymptotically. Then we found the asymptotic solution. Psi a behaves as q to the power n e to the power q square by 2. So we use the trial solution as psi of q is equal to fq e to the power q square by 2 with the restriction that if q as q tends to plus minus infinity is finite. And lastly, we found that the differential equation that is satisfied by the function f this is what we have done in this class. Before attending the next class, you please go through Harmonic differential equation and Harmonic polynomial. The next class will entirely depend on the property of harmonic or of the Harmonic differential equation.